Hello friends, welcome back to my channel. So today we are going to start important topics from Hui, and I will try to cover these important topics from other books also, right? So you will get complete information here. In this video we are going to take important points about lattice energy. We will not go in the basics of lattice energy, but we will take only important things, right? Then we will move on to the polarization or generation of covalent bond. We all know about Fajans rule, but I will take some important questions, and using these questions you will easily understand what is this polarization effect. Right, so first thing is lattice energy, and we will discuss how we can generate this Born-Lande equation. So what lattice energy, the terms include lattice, means when we are going to construct a lattice, then the amount of energy will be released, right? And this energy released is called as lattice energy. And this, how this energy is going to release, we will see it like this. Suppose we have a cation and an anion, right? These two are separated by each other by infinity distance, right? And when they will come closer to each other, they will form a lattice. Suppose we have a cubic lattice which contains all the cations and anions, and we are talking about only one pair here, right? But in general, lattice energy is for 1 mole of cation and anion when come close to each other from infinity distance to construct a lattice. Then the amount of energy released, this is very important, that this energy is released energy, means it will be negative in sign. So this amount of energy released will be called as lattice energy. So suppose I have a I will try to explain this lattice energy using a graph. So this is the graph between energy and internuclear distance, right? This is positive and this is negative. We all know that positive is repulsive forces and negative is attractive forces. So when these two ions are at infinity distance, there is dominantly active here a force of attraction between them, right? So we can consider it like this, that force of attraction will go like this. We have a relation between this coulombic force of attraction between this cation and anion, and it is denoted by EC is equals to Z plus Z minus E square upon 4 pi epsilon r. So if we consider only the force of attraction between these two, the graph will go like this, right? From infinity to it will move like this. And if we are going to consider that there is a repulsive force also, because these ions having nucleus will also have electron cloud around them, right? And these electron cloud can cause repulsion with each other, right? They can repel each other, and the repulsive force will be higher when they will be very much close to each other. When they will come very close to each other, then the repulsive force will act. Means suppose I have a distance here, the internuclear distance, and when they will come closer than the internuclear distance, then repulsive forces will act, right? So this is the graph when only repulsive forces are acting. But in actual situation, both type of force will go simultaneously. We have repulsive force as well as attractive force. So we have this type of graph, this one, right? And this is your, suppose, R naught, perfect the equilibrium distance between cation and anion. So why I am telling all these to you, because sometimes in exam they can ask you Born-Lande equation, and it is not easy to remember all type of equation when you are going to give a competitive exam, right? Because you have already a number of things to be remembered. So try to understand things. So if they can ask such type of equation, then you can easily calculate by considering two important things, that there is coulombic attraction forces between the ions and there is repulsive forces due to the electron. And remember, only this repulsive is B upon Rn. This B is a constant and this N is Born exponent. Its value will be given or if it is not given, then I will tell you how to calculate it. The total energy is due to this Coulombic force of attraction energy and this repulsive energy, right? These two will combine each other to give you total lattice energy. Now one more thing, we are here only considering that we have only one pair of cation and anion. We are considering that we have only one cation and one anion, but in actual situation a lattice is formed by the combination of certain a definite number of cations and anions. Depending upon their coordination number, we have a definite pair of we have definite number of cations and anions, right? And the total energy of attraction will be calculated by considering their respective distances, right? So we cannot calculate it directly. There is a constant given to calculate this total attraction energy, and it is given by A. This A depends on geometrical arrangement of cation of this lattice, right? It depends on it. So this A is called as Madelung constant. Its value will be given in the exam, right? So we have this type of equation now, and the total lattice energy having n units, n such type of units. What is n here? This is Avogadro number. Then we have to simply multiply this equation by n. A n, all things will remain as such, right? So this is the total lattice energy, and you can easily see that when these two ions, this cation and anions, are coming close to each other to the equilibrium distance, there is decrease in the potential energy of the system, right? The potential energy is going in the negative direction, decrease in potential energy. And if this potential energy is decreasing, means lattice energy obviously will be negative, and this decrease will increase the stability of the system, right? So you can predict one thing very easily, that if a system have highly negative lattice energy, it will be more stable. So higher the lattice energy, more will be stability. So what thing you can easily determine using this all concept, that you can easily calculate total lattice energy of the system having n units, Avogadro number of units, by considering only these simple formulas. There is no difficulty to remember all these, and you can easily describe that what will be the sign of your lattice energy. There should be no confusion about that, and then you can find out easily that which system will be more stable, right? Then we will try to find out this lattice energy at equilibrium distance. So we have a formula of total lattice energy as A is Madelung constant, N for Avogadro system, and then we have to apply our simple formula. This is for repulsive part, N for Avogadro system, and Rn, right? Now at this equilibrium distance, the change in lattice energy with distance will be 0, right? du over dr is 0. So we can differentiate this equation very easily, and after differentiation you will get, the differentiation is very easy. You have to simply place this r here, r minus 1, then you can do easily differentiation. Similarly, this Rn will become R minus n, right, when it will come on the above side, and here you will get, right, this will be your equation after differentiation. Now using this equation you can calculate the value of B. So B will become, this will be the value of B. Now we will place the value of B in this equation, and we will denote this lattice energy by U naught, because we are going to calculate it at this minimum distance, and this is called as R naught, right? So this U naught will be equal to, and at this point this R is also denoted by R naught. So you will get this equation, right? And here this equation is called as Born-Lande equation. So if you can remember this equation, it is very good, and if you cannot remember it, so try to follow the concepts, and then you can easily calculate this one, right? This is not very important equation, but sometime in examination they can ask you questions based on them, right? So you should have an idea about it. And what about this value of n? Sometimes they can give you the value of n in the question, but if it is not given, then for helium, neon, krypton and xenon like system, means after having cationic or positive or negative charge, the system will try to approach the configuration of these ideal gases. So we have values for these type of configuration. N is 5 for helium, then 7, 9, 10 and 12. So try to remember it that it is following that odd numbering 5, 7, 9 and then we have 10 and then difference of 2, 12, right? So in this way you can remember it. And suppose you have a system like NaCl. So for NaCl we have Na plus and Cl minus. So Na plus having the configuration 2,8 and Cl minus is 2,8,8, right? So this sodium Na plus resembles configuration of neon and this Cl minus remembers the configuration of argon. And for neon system we have N is equals to 7 and for argon we have 9. So we will take average of it and it will become 8. So N will be 8 for the NaCl. So in this way you can calculate the value of N, but most of the time they will give you the value of N in the question. So this is about Born-Lande equation. Now what we can find out using this equation, you can see that lattice energy depends upon charge and the internuclear distance. So as the charge increases, lattice energy increases, and as the distance, this internuclear distance increases, lattice energy will decrease. There is inverse relation between these two and direct relation between charge and lattice energy. Now you don't have to remember this point, you can easily apply the concept of your Coulombic force of attraction. Try to remember only that part and you can easily find out that what will be the relationship between lattice energy with charge and internuclear distance, right? Now we will try to apply this concept on certain examples. So we can conclude here that lattice energy is directly proportional to charge and inversely proportional to internuclear distance, and it is directly proportional to Madelung constant, right? So if I have an example that ZNO, MgO, AgCl and CaF2, I have these 4 salts here. So try to find out what will be the order of lattice energy. So we have here bivalent salt, this Zn plus having this zinc has plus 2 charge, oxygen has minus 2. Similarly this is also bi means bivalent. This one is univalent and the CF2 is univalent bivalent, right? So what is the meaning of it? First we will number them. So as I have said that lattice energy is directly proportional to charge. So when we have higher charge, lattice energy will be higher, means it should be highest for 1 or 2 because both of them have bivalent charge. So highest value will be for 1 or 2. We will decide later that what will be the relation, what will be the order for these two. Then we have univalent bivalent, means next number will be given to 4 and least for the 3 which has univalent relationship. Then what about these two? So charge is same. Next thing come the internuclear distance. So for Zn plus 2 the anion is same for both of them. So we will not consider anion, we will take only cation. Here we have Mg plus 2. So as we will move from left to right, radius of for this cation will decrease, and this when this, or you can say that as we will move from left to right, the size of ion will decrease. So it will be smaller in size than magnesium plus 2. And if it is a smaller, then the distance between anion and cation the internuclear distance between anion and cation will decrease. Lesser the value of R, higher will be lattice energy. So we can say that 1 will be highest, then second, fourth and third. So this will be the order. So in this way you can easily find out what will be the relationship with lattice energy. Then next point comes relationship between lattice energy and hydration energy. He is hydration energy. So what is the relation between these two? If it is given that lattice energy is higher than hydration energy, if it is given, then the salt will be insoluble in nature, right? And if hydration energy is higher than lattice energy, then it will be soluble in water. And if these two are almost equal, then salt will be partially soluble, right? So we can use this concept also. Then next point is, next we will take polarization and Fajans rule. We all know about the Fajans rule, so we will take the important point of this, right? So first I will want to give you an introduction about Fajans rule, that all the bonds are not purely ionic in nature, they sometimes have covalent character, and when the covalent character increases they are called as covalent, and when their ionic character is prominent they will call ionic. So how we will decide that covalent character is increasing? We can use this Fajans rule. What this rule says, that if I have a cation which is smaller in size and having high charge density, then it can cause polarization of an anion which is larger in size and softer in nature. So this cation can cause polarization. Polarization means distortion in the shape of this anion, and due to this distortion this bond will become covalent in nature. It will not remain purely ionic, right? So first thing is that as the size of cation decreases, charge increases, covalent character increases. Second point is, as the size of anion increases, charge increases, polarization increases, and the covalent character increases. We all know about these 2 points. Third point is very important, which will be useful for us, that when we have a configuration similar to transition metals, when cation having configuration similar to transition metals, means it has a configuration like this one, it causes increase in the covalent character. How? So we have this type of configuration for a cation, and we have another cation which has configuration similar to the noble gases, like this, right? We have 2 cations which have same size and same charge. Then how we will decide that which will have higher covalent character? How we will decide this? We can use their configuration. If it has configuration similar to transition metal, it will have higher covalent character. What is the concept behind it, right? So we know that this polarization is due to this nucleus, this positively charged nucleus, right? But in addition to this nucleus, this cation also having a electron cloud around it, and this electron cloud causes repulsion with the electron cloud of anion, means it is causing shielding of this nucleus, this electron cloud causing shielding of this nucleus. And when we have configuration similar to the transition metal ion, this shielding effect is low, right? And when the shielding effect of these outer electrons are low, this nucleus, this positively charged nucleus, can effectively cause distortion of the electron cloud of anion. So covalent character will be higher for it. So how we can apply this concept in the questions? Suppose I have 2 salts, that calcium chloride and this mercury chloride. So both of them have same charge, +2 +2, right? And they are asking you that which will have higher melting point, right? They are asking about melting point, higher melting point. So in case of it is in journal, covalent compounds have low melting and boiling point than ionic compound, right? So first you have to find out that which will have higher covalent character, and is if the covalent character is higher, melting point will be low, right? So you can decide on that basis. So this calcium plus 2 have, and this calcium plus 2 and mercury Hg plus 2, both of them have same charge and their size is almost same. So we will look at their configuration. This has configuration similar to noble gases, and this mercury chloride has configuration similar to the transition metals, right? So it will having higher covalent character, means melting point will be higher for calcium chloride. It has around 782 degrees centigrade melting point, and it has 276 degrees centigrade. Let's take one more example. Suppose I have NaBr, magnesium bromide and aluminum bromide, right? We have three salts and they are asking about the melting point again. So in all these cases, anion is same, so we will not take the anion. The cation is sodium plus magnesium plus 2 and aluminum plus 3. So as we are moving from left to right, charge increases, size decreases, means covalent character increases. So the order of melting point will be this one, right? So you can easily predict in this way. Another thing is they can ask you question like this, that you have salts of silver halides and they are asking you about the solubility of these silver halides in water. So cation is same, anion is F minus, Cl minus, Br minus and I minus. So as we are going from up to down, the size of anion increases, and the covalent character increases because charge is same. So we cannot consider the charge, and we know that as the size of an anion increases, its electron cloud can easily be distorted. So covalent character increases. So as the covalent character increases, their solubility in the polar solvents like water will decrease. So AgF will have highest solubility, then AgCl, AgBr and AgI is almost insoluble, right? So you can apply these concepts. So I have taken today very simple type of topics, but in these simple topics certain points are very important which may sometimes confuse you. So try to focus on that topics which will be difficult for you, right? So I will end today's video here. Soon I will upload a next video on different topic from the WHOI, which is important for net and gate examination. So keep watching, and if you like my videos, please share my videos with your friends. Thank you so much for watching.